fields with spin. Up to now I consider the simplest system, which is described by the scalar wave function. Phi was a scalar. And of course, for real applications, say if we consider interaction of electron with electromagnetic field, we need something with spin. Spin 1/2 like electron or proton, and spin 1 as photon. Okay? But this, in principle, generalization is straightforward. So let me start with a description of fields with non-zero spin with spin 1/2. And relativistic particle with spin 1/2, like electron or proton, is described, according to Dirac, by four-dimensional wave function. So there are functions psi of x, which have four components, psi 0, 1, 2, 3. Okay? And psi satisfies the Dirac equation. Dirac gamma is gamma matrices of Dirac. I hope that everybody knows what is it. And it is the first order equation, this one. Okay? Now, one can write down the general solution of this equation. The general solution of this equation. Yeah.
During this lecture, without comments,
without what?
Without comments, you state first C equal 1, then A equal 1, so that it's necessary to note for.
Okay. Sorry, yes, C is equal to 1, I think everywhere.
And A equal 1.
But now it's not lattice, so no A. No H.
H. And,
H, yes, sorry, yes. H, yeah, I'm sorry, yes, indeed. There are so-called atom system of units where C and H are equal to 1. So when I don't write explicitly C or H, I always assume that they're equal to 1. Yes, thank you. Okay. So the solution of this equation can be written in the following way. So alpha is the index 0, 1, 2, 3. So it takes 4 values, psi alpha. And now there is an integral. If you remember the corresponding equation for the scalar field, it looks as the same, but there was no this u and v. Then if I eliminate u and v, then it will be the same. No, there is one more difference, sorry. I considered Hermitian scalar field. And then I had here A and A dagger. Now I consider complex field, psi. So I have just two different quantities, B and C dagger. This is another difference. What are U and V? U and V are the system, some vectors which describe non-zero spin of this. So for electron, there is additional physical observable quantity, which is called spin. Well, naively speaking, it is some rotation of this electron. Of course, the elementary particle cannot rotate, but anyway, spin characterizes the angular momentum of the particle. And so this U and V satisfy this equation. K is the momentum of particle, K mu gamma mu plus M U is equal to 0, and K mu gamma mu minus MV equal to 0. And this is, okay, I have no time to discuss it, means that this particle, this wave function, or this operator, better to say, sorry, this operator describes the spin 1/2 particle. And the Lagrangian for this spin 1/2 particle, of course, is given by this equation. I psi, gamma mu d mu plus I m psi. If I vary it with respect to psi, I just will get Dirac equation. If you remember, that was this one. Okay. So this is Lagrangian. Okay. So much about spin 1/2 fields. I have no time to discuss more. Let me say now a few words about electromagnetic field. Electromagnetic field also have internal angular momentum, which is called spin. And this spin is equal to 1. And the Lagrangian for electromagnetic field, free electromagnetic field, is given by, as you know, I guess, from classical electrodynamics, square of stress tensor. So stress tensor is d mu a nu minus d nu a nu, where A is a vector potential, okay? And I should just square it. Square means, of course, summation with respect to mu nu, okay? This is a free Lagrangian. And now I can write the complete Lagrangian, which describes the Dirac field, electron, psi, electromagnetic field, this part, and then interaction. How to write interaction was known even 19th century, before Maxwell, but of course it's now written in some Dirac notation and relativistic notation. Anyway, it is psi gamma mu psi. This is electric charge E. Psi bar gamma mu psi A mu, integrate over X. So this is a complete Lagrangian which describes the interaction of a spinor field with electromagnetic field. It is more convenient to write it in this way. A is action. Action is integral I psi gamma mu. And if you write here free Lagrangian, there was just derivative, d mu. Here instead I write so-called covariant derivative. Covariant derivative is obtained from usual derivative d mu by adding the term I e a mu psi. Why it's called covariant derivative you will see very soon. Then the mass term. Mass term is the same as for Dirac field. And there is a free Lagrangian for electromagnetic field. This is in modern term the Maxwell-Dirac Lagrangian, which describes interaction of Dirac field psi, for example, electron field, with electromagnetic field. And if I vary it with respect to psi and a mu, I will get Maxwell-Dirac equations. Equations which determine the dynamical evolution of the system of electromagnetic field and electron, or any spinorial particle. This Lagrangian and this equation have remarkable properties. So now we firstly will meet the notion of gauge invariance. In fact, it was of course known people for a long time, but only rather recently, well, recently for me, maybe not for you, about 50 years ago, it was realized that this gauge invariance has a fundamental meaning in the world of elementary particles. But up to now, I'm not saying about general things, just let's make some observation. The observation is the following. The Maxwell-Dirac Lagrangian and Maxwell-Dirac equation are invariant with respect to the following transformation. Instead of psi of x, psi is a field which describes electron, I use psi multiplied by the phase factor, but phase factor with the parameter alpha which also depends on x, exponential I alpha x. Of course, the conjugated variable psi is multiplied by the same factor, but with this minus sign. And simultaneously, I make the gauge transformation for the electromagnetic fields. A mu is shifted by the gradient of alpha. Well, you can check. Of course, I guess you know, but you can, who does not know it, can easily check that the Lagrangian which I wrote at the previous transparency, as well as equations which follow from this Lagrangian, are invariant with respect to this transformation. It is very fundamental fact what it does mean. So let us firstly try to understand what it means. You see that if I change a mu by the gradient of arbitrary function and simultaneously will rotate psi, then I will get a new field. Yeah, I will, instead of a mu, I have a new field, a mu vega, which is a mu plus gradient of some scalar function. And this field describes the same physical system. So there is some redundancy. There are too many variables. A mu have too many variables, and I can use this freedom to eliminate some coordinates. Okay. For example, I can use d mu alpha in such a way that one coordinate will be equal to 0. Of course, I cannot eliminate all of them because alpha has only 1 degree of freedom and d mu have 4. But I can eliminate at least one of them. Moreover, that means that not all the components of a mu are observed. They are, in fact, dependent. And probably most of you heard about famous Noether theorem, Emmy Noether. This theorem was formulated at the beginning of 19th century, or 20th century, sorry. And it states that if you have the system which is invariant with respect to some transformation, and transformation in this sense means it's a group transformation, so alpha doesn't depend on x, so called soft quantity, charge. So this is Noether theorem. So if you have a system which is variant under some rotation, rigid rotation, then you have a conserved charge. But probably not many of you know that there is a second Noether theorem, which was proven by the same Emmy Noether, and it states that if you have the system which is invariant with respect to transformation with parameters depending on x, like here, That means that not all the variables in this system are